So the main goal in looking at section 2.6 is to come up with a way to prove a sequence converges without knowing its limit A. Right now, if we don't have a monotone sequence, then we don't have any way to prove that that sequence converges other than using the definition of convergence itself. So we want to come up with a way to avoid needing to know A, because oftentimes when you're trying to prove something, why would you even bother looking for a limit if you don't even know the limit exists first? So asking the question about whether or not you converge or diverge is like saying, should I bother looking for a limit? If I converge, then I'll look for what the limit is. We would like a way to do that. And so we had talked about this already, where we take our typical convergence picture and we know that when you're converging, there's a way to chop your tail such that you can trap the entire tail inside your epsilon band. Now this epsilon band, the way I've drawn it, this is 2 epsilon wide in terms of its width. And remember, we know that the terms of the tail are close to A. Because they're all in that epsilon band. But then we ask the question, what else can be said about them? And in particular, what can be said about them without reference to A? Because our goal is to come up with a way to think about convergence without needing to know A. So is there anything else that we can observe that would allow us to bypass the need for knowing the limits? So because any term or any 2 terms in the tail are both in V epsilon of A, they must be less than 2 epsilon apart. Since they're, since any 2 terms are in the tail, they must be less than 2 epsilon apart, simply because since the band is 2 epsilon wide. This is true for all terms in the tail, not just adjacent terms. So this actually gives us our condition that we will ultimately show is equivalent to being convergent. So I'm going to introduce this as a definition, and what we are doing is we are defining what it means for a sequence to be Cauchy, and what we will show is that Cauchy and convergent are equivalent conditions. So a sequence A sub n is called a Cauchy sequence provided for all epsilon greater than 0, there exists a capital N in the natural numbers, such that for any 2 subscripts that I pick that are in the tail, so for all little n and m greater than or equal to capital N, the distance between those 2 terms should be less than epsilon. So we're claiming that any 2 values we pick in our tail must be close to each other, and it doesn't matter how far apart their subscripts are. So if A500 and A3005 are both in the tail, then they have to be within epsilon apart. I can move my subscripts to anything I want in the tail, and this condition must be satisfied. So that's what we're saying here. This is any two terms in the tail must be close. So then something we should take a brief look at is what happens, why isn't it good enough for us to just say, require each successive term to be close to its previous term? So why isn't it good enough to talk about consecutive terms being close? The idea is that it's possible for you to be close adjacently, but have that distance accumulate over time as you move further down the list. So here's our question. Suppose we knew that for all epsilon greater than 0, there exists a capital N in the natural numbers, such that for all n greater than or equal to capital N, an plus 1 minus an in absolute value has to be less than epsilon. And so does this imply an converges? And so high level, what we're saying here is it good enough to only have consecutive terms in the tail close? And we've already answered this question. We've said that the answer is no. An could diverge it could diverge to infinity very slowly. And we said, oh, we know an example of that. It would be the harmonic series. But again, what I'm talking about with slowly diverging to infinity and this accumulation of distance over time is I could have points in my sequence where this one is close to that one, and then this one is close to this next one. But what ends up happening is I'm slowly going off to infinity. And so even though I can say that my successive distances, like say this one, is less than epsilon, all my adjacent ones are, overall, if you look at this whole growth, this is a large change, and it accumulates over time. So let's take a look at an example of a sequence that satisfies this property of having adjacent terms close to one another, but still diverges off to infinity slowly. So our classic example is the harmonic series, and the sequence in question that we're talking about slowly diverging is the sequence of partial sums. So be careful here. I'm not talking about the sequence 1 over n. I'm talking about the sequence of partial sums of 1 over n. And so those entries in that look like 1 plus a half plus etc. up to 1 over n. So we're going to take a look at adjacent terms in this sequence of partial sums. So remember that means we need to take a look at the expression Sn plus 1 minus Sn. If I write out what that is using the definition of the n plus first term, that's going to be 1 plus a half plus, I'm going to go to 1 over n, and then I'm also going to add 1 over n plus 1. And then if I subtract Sn, that's 1 plus a half, but I stop adding at 1 over n. And notice that the only term that they don't have in common, the only term that doesn't cancel in this difference is 1 over n plus 1. And we know that by the Archimedean property, we can choose capital N such that 1 over n plus 1 is less than epsilon, given any epsilon greater than 0. And if I can do that, that's just saying, hand me an epsilon, I'll hand you back the tail such that the difference in the successive partial sums is less than that epsilon value. That would show that adjacent terms are close for the harmonic series, but we already proved in class, well, not in class, but in a previous lecture video, that Sn has to diverge to infinity because you can continue to go out far enough and get more and more copies of a half every time you go out another 2 to the n terms in the partial sums. So ultimately what we will prove in this section is the Cauchy criterion, and that states that a sequence converges if and only if it's Cauchy. So that gives us a way to, if we can prove a sequence is Cauchy, then we don't need to know what the limit of an is. We don't need to know a to prove that our sequence converges. In the remaining videos for this section, we'll go over the proofs that are necessary for showing this. So we're going to split it into 2 parts. We have to prove that if an converges, then an is Cauchy, and we also need to prove that if an is Cauchy, then an converges. So look for the other videos to do that.